Saxon Algebra 1, Lesson 110. Today, we are going to draw a lot of pictures. So make sure you have paper and something to write with, and we're going to be very light on calculations, but very much into drawing pictures. Okay, we have drawn these pictures before, and these are what we call parent functions. They're like basic. All right, and there are 4 of them that we're going to draw over and over and over and over and over and over again. So the first one, we're going to be making 4 plus signs across your page. This will be the rhythm for the whole lesson. So space them out as best you can so that you get 4 across the width of your page, because we have 4 different functions that we're going to look at in a number of different scenarios. The first one is the graph of what we call a quadratic, and that means simply that it has an x squared term. It can be fancier than that, as we're going to see, but this is the basic function when you have a squared term. We call it a quadratic equation, and we call this shape a parabola. The next function, which we're going to call g, is what we call a cubic function. It's when we have a cubed term, and the graph will always look something like this. Remember these? That's the swoosh, right? So quadratic function, cubic function. I want you to identify them more by their equation than by that word, okay? Because later in your life, we are going to do more graphing of these. This, the h function, is what we call the square root function, and that starts at the origin and shoots up and over, kind of like that. And then the last one is called the absolute value function. We're going to jump down and call that the p of x. And this is the one that looks like geese flying in formation. It goes right through the middle of the first quadrant and right through the middle of the second quadrant. Remember, these are quadrants and they're numbered 1, 2, 3, 4. All right, so we call these the parent functions. They are the baseline. They show us the basic shape and the basic equation. What we're going to practice doing is shifting them in different directions. The first thing we're going to do is look at what we do to shift them up and down. So up and down on the y-axis. So these are called vertical shifts. Okay, so we're starting with our basic parent functions, and we're going to shift them vertically. Set up we're going to need 2 sets of plus signs. There's the first set, and then leave a little space because we'll be writing, and then make another row right underneath them. Okay? All right, so let's say that we want to take our quadratic function that makes the shape of a parabola, and we want to shift it up. Okay, so let's just shift it up a unit. We want it to look like this, right? We don't want it to go through the origin. We want it to go up a bump. The way we write that is now that this function is x squared plus 1. Okay, so we just tack a plus 1 to the end of the parent function. All right. How about if we want to shift up the cubic function? Well, we take our parent, which is x cubed, and again, we add 1. Oh, this is not looking all that hard, is it? If we want to take our square root function up, let's see, this is the h of x equals the square root of x plus 1. And absolute value, same strategy equals, absolute value of x, and this is a squeezer, plus 1. All right? So all we have to do with a vertical shift is add 1, and that moves it up 1 unit on the y-axis. And guess what if we want to move it down 1? Let's draw all these pictures shifted down 1. Right? See how I'm just bringing that center point down 1 unit from the parent, All of these pictures are compared to the parent, not necessarily to each other. And guess what happens to the equation? X squared minus 1. Oh, you've cracked the code, haven't you? Oh, I'm sorry, this is wrong. Absolute value of x minus 1. I accidentally made another pig house there. It's absolute value. Okay, so vertical shifts are super straightforward. If you want it to go up by 1 unit, you just add 1 to the end. If you want it to go down by 1 unit, you just subtract 1. So the number and more importantly, the sign matches the shift. This is going up into the positives, this is going down into the negatives. Bear in mind that we have horizontal shifts and their shifting is going to be a little bit different, okay? We just tack that number onto the end of the parent function and that makes it shift up and down. Okay, now let's talk about horizontal shifts. This time, we're not moving them up and down. We want to move them side to side. So let's go ahead. I want to see exactly how I spaced them. Let's make our 4 plus signs again across the page. And again, we're going to make 2 rows of them, leave a little bit of space in between so we can write the functions. There you go. And again, we're doing 2 rows because we're going to shift everybody first to the right and then to the left. All right, if we want to shift our parabola 1 unit to the right, this is what we do to our equation. Look what we did. First of all, we did something counterintuitive. We subtracted 1. You'd think you would add 1, right? Because you're going into the positive numbers, but with horizontal shifts, you don't. You subtract 1, and we didn't tack it onto the end. We put this adjustment right up close to the x. So our change, we use the opposite sign, plus or minus, and then we attach, and I know this sounds weird, we attach the change to x. We bring it right up close, tucked inside. With the vertical shifts, we just left it hanging off the back end, didn't we? We just tacked it onto the end. But here we bring the change right in close to the x. You'll see it in the other ones as well, the other functions, okay? So horizontal shifts have 2 things about them that look kind of weird and kind of different. So let's practice with the other ones. Okay, here comes our cubic function. It's g of x equals x minus 1 cubed. So it works exactly the same way as this. We use the opposite sign that you would expect. We moved it positive, but we're subtracting 1. And we attach the change to the x. All right, square root looks kind of like that. The h of x equals, and look again, we attach the change to the x, and we use the opposite sign for the change. And then here's our absolute value function. Same rule. The p of x equals the absolute value of x minus 1. That's weird, isn't it? But we use the same rules to do the horizontal shifts in the other direction. If we want to shift it to the negative side of the x-axis, we use the opposite sign and we attach the change to the x. Same two rules. So this time, because I'm going in the negative direction, I need a positive here. It's weird, isn't it? I know. Cubic, same rules. X plus 1 cubed. And here we go. This is the p of x. Absolute value of x plus 1. You'd think it would be minus 1. That's logical, but horizontal shifts are backwards. Okay, so we've reminded ourselves of the basic parent functions. We've figured out how to do vertical shifts, which is super intuitive. The up and down shifts are super intuitive. If you want to go up one, you add, you just tack it on. If you want to go down one, you subtract, and you just tack it on to the end, like we did here, right? It just adds on to the end. If you want to do a horizontal shift, side to side, it gets a little surreal. We use the opposite sign, and we have to bring that change right up close to the x. We attach the change to the x. That's what I mean by that, rather than just letting the change hang out on the end. Now, there's a third category of changes, but it doesn't have two styles. These are called reflections. They have a fancy name. Reflections about the x-axis. And I'll draw you the picture and you'll understand what I mean. Okay, so we draw 4 more of our beautiful graphs. And this time, we're going to reflect back in our mind to the parent functions, and we're going to turn them upside down. So instead of the parabola being up, we're going to make it go down. Instead of this curve being like this, we're going to start it on this side and have it go over here. Whoa, that's trippy, isn't it? Instead of the swoosh going up and over, the swoosh is going to go down and over. And instead of the absolute value going up, we're going to make it go down. So the shapes are the same. We're just reversing everything. We're creating a reflection. So if you think of the x-axis as a mirror, we're taking the mirror image, right? This one's the hardest to see. These are pretty easy as well. All right, let's look at what happens to the equations when we do this. Minus sign. The minus flips it upside down. And notice that the minus sign here, you'll see it better in this one. Let me write this one out. The minus sign doesn't need to attach itself to the x. It goes outside. When we have these shapes, it's going outside. Here, it doesn't really matter because we don't have any shape to put it inside or outside. But here we see it's just outside of these shapes, the radical sign and the absolute value signs. So that minus sign means it's just chilling out there. All right, so if we want to shift it vertically, up and down, we know how to do that. If we want to shift it side to side, we know how to do that. That's got weird rules. If we want to create the mirror image, we know how to do that with a minus sign. What we're going to do in our examples, and there are just a couple of them, we're going to look at graphs, or let's see, we're going to look at equations, and we're going to sketch the graph of them. All right, so let's do that. I was skipping over the examples as we went. We'll do them all at once. Example 110.1. Sketch the graph of this function. Okay, so the first thing we have to do is decide which kind of shift that it is. We can see we've done something. It's not the parent function. It's an absolute value function, and we're adding 3. Now, what we notice right off as we write it down is that this change is not attached to the x, right? It's not in the absolute value lines. It's out here on the edge, just chilling by itself. That tells us that this must be a vertical shift, the chill kind, right? Because it's hanging out here by itself. If it were inside here, we would know that was a different story. That's one of the weird ones. But this tells us, because it's just chilling out here by itself, we know, okay, you're the chill kind. So all we have to do, and that's a vertical shift. Vertical shifts are the chill ones. So let's draw ourselves a little picture. And we want to go up 3. So here's the beauty of these, you guys. I don't have to count 3 lines. It doesn't matter. I can just go like this, and I can write 3, and then I draw my absolute value function. This is the right answer, okay? We had to recognize, oh look, it's a vertical shift. We know it's not horizontal because then it would have to be on the inside of the absolute value signs. So it's a vertical shift. We draw it. We do not have to make it to scale. We can just say, oh, look, that's 3. Beautiful, right? And sometimes it helps, if you're confused about it at all, sometimes it helps to remember what the parent function looks like. Oops. You can reference your notes, although I really hope at this point you can draw these parent functions from memory, all right? So between recognizing the parent function and recognizing that it was a vertical shift, we're able to get the answer, and guess what? It is correct. .2 is this. F of x now equals, all right, we see that there's a change, and we say to ourselves, aha, this change is attached to the x, right? It's not just chilling on the outside, it's attached to the x, so that tells us it's a horizontal shift. And that clues us in, remember it's going to be the opposite sign, right? That's what horizontal shifts do that blows our mind a little bit. So as soon as we see that that 3 is attached to the x, it's living in the pig house there, not just chilling on the outside, we know what we're dealing with. So, and again, if it helps us, we can visualize the parent function. It's a square root function, so we know it goes like that. So you don't necessarily have to write this on your page if you feel comfortable, but you definitely have to see it in your head, because that's what we're going to be working with, right? So we draw our box, our chart. We know it's the opposite sign, so we're shifting 3 units in the positive direction, even though that's negative. We know that's how it works. We're going to the positive direction. I do not worry about scale. And then I draw my little square root function picture. And this is the right answer. They're kind of cute and fun, aren't they? All right. We'll squeeze one more on here. I'll bump my book up just a little. Ready? Number 3, sketch the graph of f of x equals minus x cubed. Aha! All that's changed is we have a minus sign in front, so that tells us this is a reflection. It's a reflection on the y-axis, or the x-axis rather, because that's the only kind we've learned, right? The top to bottom. This is the x-axis. So when we say it's reflected about the x-axis, that means x is the mirror, okay? You could reflect on the y, but we're not getting into that. Okay, so parent function, let's see, this is a cubic function. So the parent function is this thing. Just to remind me of how the picture works. So that is in my head. And now I have to do the opposite, the reflection of it. And I remember this is the one that's kind of mind-blowing to draw. It always helps me to start drawing the picture by imagining the parent, which I have right here. That goes like this. So the reflection goes like that. If you think of it, right, this is down underneath where it was, and this goes up. If you think of it almost like a solid object that you can pick up and spin, that kind of helps, maybe. Okay, so this is our picture. This is the negative. We don't have to put any numbers on this one because we're not shifting it units. We're just turning it, we're reflecting it. Beautiful. And one more. And this last one is called a combination because it's going to combine, these are the 3 different types, right? Verticals, horizontals, and reflections. This problem is going to combine them. What? John, how smart do you think we are? And John says, you're pretty darn smart. Okay, f of x equals minus the absolute value of x. We look at that and go, oh, that's a reflection, but also that. Not attached to the x, but hanging off the end. So we have 2 things going on here. This tells us it's a reflection, and this tells us it's the easy kind of shift, which is a vertical shift. So we're going to do 2 things at once. We're going to reflect it, and we're going to flip it down, and we're going to shift it up, apparently, right, on the axis. All right, so let's remember what our parent function looks like. This is an absolute value, so that's this. It's the flying geese formation, right? So now we've got everything we need to be dangerous. Here it is. So this is the way I would do it. First, make your vertical or horizontal, if that were the case. Make that adjustment first, and then right before you go to draw the picture, flip it in your mind. So we want to go to +3. I'll put it here. Right? It's a vertical shift. That means up and down. And then we want to go upside down. So that is the picture of our function with a combination of changes. And this is correct. All right? There really is no calculation in these. They're just art projects. You just have to remember the rules for figuring out which kind of a shift or reflection you have, and then use your parent function to draw a cute little picture. I hope you will enjoy this as a little change of pace. It is very different from a lot of the lessons we've had, and it's kind of one of a kind. We're not going to build on this year at all. So just enjoy drawing these pictures, and I'll see you next time. Thank you. Goodbye.